reaction conditions. That's how the mechanism is developed. कि हम चाहते हैं कि डिटरमाइन करना है क्या एक रिएक्शन एसोसिएटिव पाथवे से या डिसोसिएटिव पाथवे से रिएक्ट कर रही है. तो कई बार स्ट्रेट वे आंसर काइनेटिक्स दे देता है और कई बार स्ट्रेट वे आंसर नहीं भी होता है, बिकॉज अगर एक रिएक्टेंट की कंसंट्रेशन बहुत ज्यादा है, particularly if solvent is reacting, solvent is one of the reactants, then obviously its concentration will not change with time much. Its concentration almost remains invariant. And in that situation, kinetics of the reaction can be misleading. That reaction may be appearing as first order, but actually it may be second order reaction. So therefore you cannot take kinetics on its face value. कि अगर एक रिएक्शन का काइनेटिक्स आपको फर्स्ट ऑर्डर बताता है, तो यू cannot jump to the conclusion that this reaction is following a particular mechanism. So therefore you have to study the detailed how rate of a reaction is changed or is dependent on various factors. For example, you change the polarity of the solvent, you change the solvent, you make more solvent more polar, and then you study how the rate of the reaction, whether it increases or decreases. And we all know that if the reaction follows an SN1 mechanism, then there is formation of an intermediate, which is say 5 coordinated intermediate, and which may require solvation, which may be stabilized by solvation. And if you decrease the polarity of the solvent, the solvation may be decreasing, and therefore rate may be decreasing. So one can develop an sense that how the rate of the reaction increases or decreases with change in the nature of the solvent. That's one. And then we can change the nature of the leaving group. If you study a series of reactions under identical chemical reaction conditions, with only difference that the leaving groups are different in at different reactions. So incoming group, the taking group is same. So if the rate of the reaction does not change with the change in the leaving group, then obviously it's following a first order the SN1 mechanism, because in the SN1 mechanism or in the dissociative mechanism, the first step, the leaving group, that is the slow step. And if the rate of the reaction depends upon the nature of the leaving group, it is definitely the SN1 mechanism. If the rate of reaction does not depend much on the nature of the leaving group, then obviously it is second order SN2 mechanism. So then that is another aspect, that nature of the leaving group will give us some idea about how the mechanism, how the reaction is proceeding, whether it is following a dissociative mechanism or associative mechanism. Then you have the silent ligands, that those ligands which are not involved in the substitution but are there present in the complex. So if you change the nature of those ligands, make them more electron donating or more electron withdrawing groups, then how the rate of the reaction changes with the change in the electron inductive effect, in electron donation or electron withdrawing power of the ligands which are not directly involved in the substitution reaction. That will also tell us, the indicate us whether the reaction is following a dissociative or associative mechanism. And then ultimately we can also change the incoming group. If the incoming group is changed and the rate of the reaction changes, then it is obviously associative mechanism. And if it is not dependent on the nature of the incoming group, then obviously it is SN1 mechanism. So another thing is that you study the exchange reaction, isotopic labeling. Say water is incoming group, you introduce an the outgoing group is also water, incoming group is also water, and you label the incoming group by an isotope which is not a common isotope, and then see how the rate of the reaction, what is the rate of the reaction, what is the rate of the exchange of the isotopic atom. So that also is used to determine the slow step of the reaction or the rate determining reaction. We'll see these examples in the coming slides. So pathway of a chemical reaction is far more important than the structure of the reactant or product. in initial days of the chemistry, or the determination of the structure of a compound was predictive with small number of, obviously the sophisticated instruments were not there, and they were only tentative ideas. The tools were limited, so therefore the predictive how to predict the structure of the compounds, you cannot characterize and a compound fully by the sophisticated techniques, though those were not initially available. So only through the reaction conditions and output, no one was one was able to draw the mechanism of a reaction. One was able to draw the mechanism of the reaction. So reaction conditions, synthetic output, possible side products, possible environment harm, etc., could not be predicted. Clarity of the mechanism of the reaction helps to understand the electronic structure of the reactants and products and their interaction. And you can predict how a different reactant will react if you understand the mechanism of a reaction. So a mechanism also helps to predict about the synthetic methodology for any new reaction or overall control of the reaction. That is the purpose of studying the mechanism of the reaction, in fact. So mechanism of a substitution reaction. Substitution reactions are those reactions in which an attacking ligand replaces an previously attached ligand to the substrate. The ligand that departs from the complex is called leaving group, and the ligand which takes the position of the leaving group, is called the incoming group or substituting group. So mechanism, then the octahedral substitution reactions involve supplement of one ligand by another. So it should be substitution or supplement. Since ligands can be treated as negative point charges or dipoles, they are assumed to be nucleophilic in character. Therefore, substitution reactions that result by replacement of one ligand by another is called a nucleophilic substitution reaction. So attacking ligand can attack a substrate by several ways to produce this substituted product. Therefore, we can have several mechanisms by which this type of reaction can occur, but we will consider only four broad types of mechanisms. Unimolecular nucleophilic substitution, SN1, are also called dissociative mechanism. Bimolecular nucleophilic substitution, SN2, or associative mechanism. Interchange reaction, dissociative nucleophilic substitution reaction, and associative nucleophilic substitution reaction. This should have been small a here. Associative and dissociative means the reactions are basically bimolecular, but in the first case, dissociative means the bond breaking is faster than the bond forming, and in the second, bond formation bond formation is in the bond formation in the second case is faster than the dissociation step, but both are acting simultaneously. So the first one, this mechanism involves two steps. The first step involves slow heterolysis of the metal ligand bond, leaving group to produce a 5-coordinated intermediate, which undergoes rapid combination with nucleophile in the second step. So the complex first undergoes dissociation and then loses a ligand to form a 5-coordinate. This I have said several times. So trigonal bipyramidal geometry or square pyramidal geometry. Out of these two geometries, square pyramidal has somewhat lower energy than this trigonal pyramidal. There is minimum change when a compound goes from octahedron to the square pyramidal. Inclusion of new ligand on it produces 6-coordinate ligand. So that's the two-step process represented here. The first step involves slow and second step is fast. Therefore, rate of reaction depends on the flow. First step, slow step, and it is unimolecular. Therefore, rate is first order in the complex, where K is the rate constant for the forward step in this step 1. Hence, SN1 mechanism is first order. That is, when we consider its kinetic aspect, we can call it unimolecular. The polar solvents favor the SN1 mechanism because it helps in ionization. It also has been observed that low concentration of nucleophile as well as the weak nucleophiles also favor the SN1 mechanism. So then the SN2 mechanism, it's a one-step process where separation of halide ion and attack of the nucleophile occur both simultaneously. This mechanism, new ligands first adds to the complex to form a 7-coordinated intermediate, which then depart in which from which one ligand departs then in a fast step to generate a 6 coordinate substituted product. This is also a sort of two-step in case the reaction rate depends upon the first step upon the concentration of the complex as well as concentration of the incoming group. Hence, SN2 mechanism is second order and is bimolecular. However, when the solvent itself acts as a nucleophile, for example, water or alcohol, the reaction shows first order because solvent is in such a large concentration that its concentration does not change with time and it literally remains constant. Therefore, kinetics there is misleading in such reactions. Non-polar solvents favor SN2 mechanism. It has been observed that high concentration of nucleophiles favor SN2 mechanism. In between two extremes of nucleophilic substitution reactions that would dissociative and associative, an interchange mechanism can also exist. What is interchange mechanism? The ligand first attacks the substrate, forms an sort of ion pair. The incoming ligand has not bonded itself to the metal, but formed a loose associate called an ion pair before breaking up the leaving group from the metal complex. Then the reaction is called interchange reaction. If the degree of assistance of the nucleophile is small, reaction is primarily undergoes dissociative pathway. Then the reaction is called dissociative interchange. If uh, the bond breaking is faster than the bond formation step, then it is dissociative. While if the reaction is more tilted towards associative reaction, that is bond formation with Y is faster than the bond breaking with the X, then it is associative interchange mechanism, right? So there is very thin line, borderline between associative interchange and dissociative interchange. Now, the types of intermediates formed during SN1 and SN reaction 1, the mechanism, two types of intermediates can be formed. Bond MX dissociates, causing least disturbance to the remaining 5 coordinate intermediate, which is square pyramidal. So if there is least disturbance to the octahedron, then the intermediate must be square pyramidal. The intermediate then is attacked by the Y and produces the 60. So this type of intermediate must lead to retention of the configuration. But if you have a cis trans isomer, then the incoming group joins the complex at the same site at which the leaving group leaves. So if you have a cis isomer in the reactant, product is also a cis isomer. If you have a trans isomer in the reactant, product is also a trans isomer. If this is the situation. This is octahedron, then one of the ligand leaves, and then in the fastest step, the ligand. The MX bond dissociates, and remaining MX5 adjust the bond angle to produce a trigonal bipyramidal geometry. So the second type of intermediate in the dissociative mechanism is trigonal bi. Then if this is the intermediate, then there will not be retention of the configuration. There will be, if you start with cis, you may have the trans as well as cis isomer in the product. Similarly, you start with trans, you may have mixture of cis and trans in the product. So since trigonal bipyramidal intermediates need some more energy for the interconversion of this movement of the two bonds, whereas no such movement is required during the formation of the square pyramidal intermediate. Hence, square pyramidal intermediate is generally formed in SN1 mechanism. However, SN1 reactions proceed through a trigonal pyramidal also, where the formation of pi bonds is possible, right? So SN2 mechanism, two types of intermediates, Y nucleophile attacks, octahedron is a configuration, is a geometry which has 12 edges, 8 triangular faces. So if the incoming group attacks Y, attacks one of the edges of the octahedron and forms a pentagonal bipyramidal intermediate shown below. If it attacks either through on the face, through a face, center of the face, then it forms a different intermediate, or if takes the complex through center of one of the edges. So there are two situations. So if the attacking group attacks Y attacks the octahedron through the center of an edge, then it forms a pentagonal bipyramidal intermediate. This is how it forms a pentagonal bipyramidal intermediate, and then it loses an X in the first step, forms in hexacoordinate complex. The nucleophile Y takes through the middle of the one of the triangular faces of the octahedron octahedron. Remember, octahedron has 8 triangular faces. So it forms an octahedral wedge intermediate. This type of situation is there, in which both attacking group as well as leaving group are present in the equivalent position as shown below. So this is lower having lower. This is having lower energy than the pentagonal bipyramidal. Then the X, moves is removed in a fast step and regenerates the 6 coordinate complex. Since pentagonal bipyramidal requires movement of the 4 ligands to adjust the incoming nucleophile, this increases the energy of pentagonal bipyramidal intermediate, while octahedron wedge requires minimum movement of the ligands, and that's why ligand-ligand repulsion are less in this than the pentagonal bipyramidal. This indicates this SN2 reaction preferably proceeds via this octahedral wedge intermediate. So now, what are the factors which affect the mechanism of a nucleophilic substitution reaction? Number one is the effect of the substrate. With the increase in positive charge, if you have a complex and the complex is having a positively charged complex ion and negatively charged counter ion outside the coordination sphere. If you increase the positive charge on the complex, then metal ligand leaving group strength also, uh, the metal leaving group bond strength also increases, and therefore bond breaking of the leaving group becomes difficult, and incoming group attack over the substrate that supports the SN2. So if you increase the positive charge on the complex, then SN2 mechanism is more favored rather than SN1, because in the SN1 you are removing a negative charge ligand away from a positively charged complex. So that becomes progressively more difficult as the positive charge on the complex increases. Rather, the attack by an incoming group to the positively charged complex ion becomes easy. So that's the effect of the charge on the complex ion, that the moment you increase the positive charge on a complex ion, SN1 mechanism is discouraged and SN2 mechanism is encouraged. Similarly, a small ionic radius of the metal ion also supports SN2 mechanism, high steric crowding. If you have more crowding around the metal ion, ligands are bulky, so that incoming group finds it difficult to attack the metal. So that supports the SN1 rather than the SN2 mechanism. So, effect of nucleophiles. The rate of nucleophilic substitution remains unaffected by the presence of nucleophile in the case of a dissociative. If a complex is following an SN1 mechanism, then obviously the rate of the reaction is independent of the nature of the strength of the nucleophile, incoming nucleophile. So increase in concentration or increase in the change in nature of the nucleophile, if that is not affecting the rate of the reaction, then obviously it is SN1 mechanism. However, if there is change in the rate of the reaction with change in the concentration of the nucleophile, or there is change in the rate of reaction with change in nature of the nucleophile, then the reaction is following an SN2 mechanism. So this is another impact. Then the leaving group, a better leaving group prefers a unimolecular nucleophilic substitution reaction, because before a take of nucleophile, leaving group has tendency to break itself from the substrate. So if your leaving group is better leaving group, then it favors an SN1 mechanism. If leaving group is not a good leaving group, the bond is not breaking easily, then it must follow the second order, the SN2 mechanism. So a polar solvent helps to break the leaving group from the substrate and therefore supports SN1 mechanism, while non-polar solvents without presence of solvent reaction prefers an SN2 mechanism. So that is all about the general reactions of the substitution reaction. Now let's go to the kinetics. Now, 3 types of nucleophilic substitution reactions, and differentiation among them is a big task. Therefore, there are 3 types: are dissociative and associative and interchange. Let's discuss the mechanism and kinetics of each of these. So dissociative nucleophilic substitution reaction involve two-step process, as I said. This should be small. This should be bigger one. Or if it is for the first arrow, then it should be small k. The first step, leaving group breaks. This is same thing. Now, the rate of the formation of the product is uh, this should have been the single arrow k2 ml5 and y. If it is if first step is fast and second step is slow. Um, but the concentration of intermediate is not known at any instant of the time, so its concentration could be determined by in terms of the concentration of the starting materials. So ml5 is formed in the first step and disappears in the second step. So there's a method in the kinetics which is called steady state approximation, that if you have an intermediate formed in any reaction, then we presume that its rate of formation is equal to the rate of the decomposition. And at equilibrium, it does not survive. It does not survive at all because it is formed at the same rate, it is decomposed at the same rate. So the intermediate in this case is formed, the rate of formation of the intermediate, it is formed in the first step, K1, and minus K1 represents the rate of the reverse reaction, that this intermediate and X combine together and form back the original complex. And then it's also decomposed by the second step where the intermediate reacts with the Y and forms the product. So intermediate is formed in the first step in the forward reaction. Intermediate is decomposed or consumed in the reverse step of the first step, and intermediate is also consumed in the second step. So, if applying steady state approximation means that its rate of formation is equal to rate of decomposition. So, condition we will reach where the rate of formation and disappearance of ML5 will be same. So, this state is called steady state approximation. So, applying steady state approximation, we have this equal to rate of formation of the net rate of formation of the intermediate is zero because its formation and decomposition is same. So you use this equation, ml5 and ml5 are common, and take it common, take it first one side. So write k minus 1 ml5x plus k2 ml5y and equal to k1. Then take the common ml5, which is the intermediate. It is k minus 1x plus k2y is equal to k1. Then ml5 concentration is equal to k1 ml5x divided by this part, k minus 1x plus k2y. Then now rate of the reaction depends upon the concentration of the ml5 and the y. Therefore, you place the value of this in this equation. So k2 into ml5, it is k1, then whole thing. This is the final equation for rate, general equation for the rate of the reaction. Now we apply different conditions. If the K1 minus K2 is second step is very fast, then the first step, the reverse of the first step, then in the denominator, you can neglect this part, the reverse part, because this is very large. Then K2 and K2 cancels, and Y cancels, and you are left with K1 into this. So it's a first order reaction. This is subject to the condition that the mechanism follows a first order reaction, that reaction is happening in the first two steps. The first step is reversible, so there is equilibrium. The second step is very fast. If the second step is quite fast, then the reaction must be independent of the concentration of the entering group. It must depend upon the concentration of only the starting material substrate. So that is first order rate. That is how the kinetics of an SN1 mechanism is developed. Now, associative nucleophilic substitution is also a two-step process in which the step first ligand associates with the complex and forms a 7 coordinate, and in the second step it decomposes. This should be a single arrow. in the forwarded. This is K1, this is minus K1, and this is K2. So same thing will be applying here. The rate of formation of the product is K2 ml5xy. And again, this is intermediate. Again, this is formed in the first step, forward step. It is decomposed in the reverse step, in the first step, and also it is decomposed in the seconds. So applying same procedure of steady state approximation, the formation of the rate of formation of the intermediate, it is K1 forward step first, reverse step first, and minus uh, you know second step. Minus because it is consumed in the reverse process here, consumed in the second step. So again, applying steady state approximation, which says that if an intermediate is very reactive, then its rate of formation and rate of decomposition must be same. So the overall net formation of this is zero. So you equate this equation equal to zero. Again, take ml5x common, and you will find out it is equal to k1, the initial substrate, into y divided by k1 minus k minus 1 into k2. So putting that equation into the original equation, this is the equation. So this is the rate constants divided by rate constants. So you can combine them, k1 divided by k minus 1 and k2 into a single rate constant k. So this is k2 into k into this ml(x). So this is a second order reaction in all ways. It's a bimolecular reaction. It is first order in the substrate and also first order in the Y. So this is how the mechanism of the second order reaction is developed. The kinetics of the mechanism second order reaction is developed. Now, then we go to the interchange mechanism. This is a bridging mechanism between SN1 and SN2, in which the taking ligand Y forms an inert pair, ion pair with the substrate, and then leaving group X breaks to form the ML5X. So again, you can have this same type of situation. Rate of reaction is K2, this intermediate. Again, you will use this steady state approximation. But now the intermediate, the total concentration of the reactant can be written as the unassociated, and some part of it will be forming an ion pair, because this is not a sort of reaction. It is just a loose association of the substrate with the incoming group. So if I say that M0 is the total concentration of the reactant substrate, then a part of it is in the free state and part of it is present in the form of a ion pair. So ML5 X, this is the original substrate, is equal to M0 minus this ion pair. So if you use this in the equation, then see K1, this in place of ML5 X, I will write this M0 minus ML5XY. This will remain ML5XY. This will remain as ML5XY. So the first, this will be K1 M0, this into Y, then these two remain same. This is K1. Now you open it, K1 M0 and then Y minus K1 ML5XY into Y. This K1 K minus 1 ML5XY, K2. So you have ML5XY in three terms, 1, 2, and 3. You take common ML5XY. So this becomes equal to K1 M0Y divided by K1Y. This is this one plus K minus 1 plus K2. So putting this value in the equation, the rate of reaction depends upon K2 into the intermediate. Then you have the K1, K2, M0, the original concentration of the complex Y divided by K1 into Y plus K minus 1 in K2. I've written this again here, same equation. So dividing both numerator and denominator by K2. If you divide numerator by K2, this K2 is gone. We're left with K1 M0 into Y. In the denominator, you have K1 by K2 here. You have K minus 1 by K2, and here 1 simply. So I've designated them K1 by K2 as K, K minus 1 by K2 as K dash, K1 by K2 as K, and K minus 1. So this becomes then the rate becomes K1, My, M0, Y into this, these constants into Y, another constant plus 1. If the ion pair is formed, but dissociation mechanism is more favorable, right? So if it is a dissociative ion pair interchange mechanism, that is, the bond breaking is much faster than the bond formation. So then K2 is much higher value than K1, and because of the high concentration of Y, at any point of time, Ky is much larger than the one. So one can be neglected. So K dash can be neglected. So it's only Ky in the denominator. If that is taken into the consideration, y and y go, it is k1 by k1. This can be written as k can be written as k1 by k2 because it was originally k1 by k2 into y. So other this k dash can be neglected. One can be neglected in that situation. Then k1 and k1 goes and it becomes k2 m0 because y and y also go. So that becomes k2. What is m0? It is the ml5, the free complex plus the ion pair. So it's sort of a first order reaction. So this is dissociative interchange. The rate of the reaction does not depend upon the y. It only depends upon the free substrate plus concentration of the ion pair substrate, right? So as a result of which it will seem to follow the first order kinetics, though y appears in the rate law equation, but it appears in the ion pair, not as independent y, right? So as a result of which the reaction seems to follow the first order kinetics. Such reaction mechanism is dissociative interchange mechanism and represented by ID. Similarly, if the reaction is bent towards SN2 reaction, then concentration of Y it cannot be neglected in the equation, and in such case, it will have the SN2 mechanism by molecule. So then we have exchange reaction. If all nucleophilic substitution reactions, if X and Y are become identical, then the rate type of substitution reaction performed is called the exchange reaction. So this is an example: aqua complex and water coming inside. So this is isotopically labeled so that you can identify whether it has gone inside or substitution has happened or not. So if one can scan the rate of hydrolysis of various octahedral metal complexes, the various complexes can be divided into following categories. Category 1, on the basis of the rate of this self-exchange. In some complexes, water gets uh, exchanged quite fast, and in some case situations, the water gets exchanged with the same water inside the coordination very slowly. On that basis, that reactivity basis, the metals have been divided into three categories. Category 1 is the rate of exchange of the coordinated water is very fast. The rate constants are of the order of 10 raised power 8 per second. Generally, these rates will be obviously first order because the incoming group is water, which is solvent, and its concentration is so large that it does not change with time. So you cannot monitor its concentration. So what are the metals in this category? These are alkali metals. One step down, and on stepping down the group, the size of the cation increases, and consequently the charge density on the metal decreases. So metal water bond becomes weak, and hence bonds are easily broken. Therefore, the rate of the reaction increases as we go down the group. For second group alkaline earth, charge density is larger, hence metal water bond is comparatively greater, and rate of exchange is somewhat slower than what is observed in the alkali metal ions. In general, even the faster kinetics fail. So you don't have the techniques, you can't monitor the kinetics of these reactions by traditional tools. Special techniques, fast flow methods, automatic techniques, even those techniques fail to monitor such reactions because reactions take place in microseconds. 10 raised power minus 8 is the 10 raised power 8 per second is the rate constant. This huge rate, fast reactions. So this then second category is dye positive transition metal ions, And the among the alkali metal ions, the metals like the magnesium, which has very small size and therefore high charge density, and because of this high charge density, the metal magnesium water bond is very strong and therefore breaks very difficultly, and therefore the substitution, the exchange reaction is very slow. And also some tripositive ions, the bonding in these complexes of these ions is somewhat stronger than that of the complexes in the class first, but crystal field stabilization energies are somewhat smaller. The charge z square by r for these metal ions ranges from 10 to 13 coulombic square per meter. The rate of exchange of the coordinated water is fast, that is 10 raised power minus 5 to 10 raised power 8 per second. The reactions have been studied by fast techniques in which equilibrium is perturbed by a fast variation of the physical parameter like pressure or temperature, and then the response of the system is used to estimate the rate of the reaction. So there are techniques now developed known as fast flow, flash flow techniques, in which the change in concentration is monitored by a special fast flow techniques, and these reactions have been monitored now. Now, the category third is the rate of exchange of the coordinated water is slower. It is the rate constant has 1 to 10 raised power 4 the magnitude. These include tripositive metal ions stabilized by crystal field stabilization energy. Therefore, they react slowly. Two very small ions, beryllium and lanthanum ions, also form lanthanum La, fall in this category because they are also too small and therefore bonds are very strong and they react slowly. Z square by R of these metal ions are found greater than 30 coulomb per meter as coulomb square. As compared to class first and second, the exchange of water is relatively slow, although first order rate constants have been found to range from 1 to 10 raised by 4 per second. For transition metal ions, substitution rates decrease across the series. As you go from left to right, the size decreases. For example, manganese has greater. This is role of crystal field stabilization energy. This is because the increase in the effective nuclear charge on moving from the left to right in the series. Uh, so the substitution becomes difficult as we move from left to right because of the decrease in the ionic size. And then the crystal field stabilization energy has also its role. As I said in the earlier lecture, all the substitution mechanisms that we will be studying or we are studying have been developed by studying the copper 3 plus cobalt 3 plus complexes in the low spin state, that is D6 complexes, because they have the highest crystal field stabilization energy and therefore they react slowly. They are inert, and because of the small high charge density and also because of the high crystal field stabilization energy. So as you move across the period in the 3D series from left to right, if the charge is same 2 plus 2 plus or 3 plus 3 plus, then the rate of the reaction decreases from left to right because size decreases. This is because the increase in the effective nuclear charge on moving from left to right in a series, and also the ligand field stabilization energy affects the rate of exchange here. It is possible to follow the reaction by traditional kinetics, but augmented with the flow techniques. Then category 4, the rate of exchange of coordinated water is very slow, 10 raised per minus 3 to 10 raised. These are literally inert complexes. They are chemically inert complexes. This category includes chromium 3, cobalt 3, rhodium 3, iridium. See, cobalt 3, rhodium 3, these are all D6. Platinum is also very rare. D3 is chromium 3 is also D3, having high coordination, high ligand field stabilization energy. The rate of exchange of water is depending on the size of the cation as well as the crystal field stabilization energy. D3 and D6 ions are most inert. For example, rhodium 3, low spin, it must be D6, it's not D7. It is rhodium 3. Uh, Cobalt, rhodium, iridium. No, it's D6. It is D6. Chromium is D3. Cobalt 3 is D6. Rhodium is just below the cobalt in periodic table. So to trace the reason for such reactions, students can direct themselves to module, and where we have discussed the various crystal field theories. You can develop its own, and we have developed in your previous lecture. We developed a table that which configurations are supposed to be reactive and which are supposed to be less reactive. Then uh, then let's go to the substitution reactions in the octahedron complex. Solvent. In most substitution reactions, solvent interfere nucleophilic substitution reactions. Therefore, before a take of nucleophile substitution, a solvent replaces the leaving group and forms a different complex, which not only affect the substitution but also provide a wrong information about the kinetics of the reaction. So kinetic studies on the substitution reaction of octahedral complexes have been studied in aqueous solution. Rate of substitution reaction in aqueous solution can be affected by pressure. So acid and base hydrolysis. The main reactions, 3-4 reactions we have to study, that we will study next time. Number one is acid hydrolysis. Number two is basic hydrolysis. The third one is the equation reaction. One acid-base hydrolysis. They are commonly known as, also known as equation reaction. These are reaction in which a negatively charged ligand will be displaced by water molecule if it is the neutral medium. If it is acidic medium, by again by water, and if it is basic medium, by the OH negative. These reactions are generally classified as equation reactions, and they can be also as called acid hydrolysis or base hydrolysis, depending upon what is the pH of the medium. Then you have anation reactions. Anation reaction means when an anion is substituting in water molecule. Reverse of the equation is called anation. That we will discuss next time. Uh, Today it is enough. So if there are any questions,